What's up, guys? It's a beautiful day in the neighborhood, and we've got chapter 5.
We are Lodge, Jordan, Warren, Hopkins, and Wood, the best pentane you've ever seen.
If you guys remember this chart from chapter 4, we went from isomers to stereoisomers to configurational isomers. But if the configurational isomers have a mirror image, it is an enantiomer. If it does not, it's a diastereomer. Like I said before, an enantiomer also has a mirror image, and a diastereomer does not have a mirror image. Based on this molecule, this is a mirror image of this one. An enantiomer is always non-superimposable. As you can see, the mirror image, whenever you overlap them, you can never get the same molecule. As you can see here, if we match up the blues, the whites and the greens will always be switched.
In this section, guys, we're going to be talking about how to draw mirror images. As you can see in this molecule here, we have carbon as the central atom, bound to 4 different substituents: hydrogen, chlorine, fluorine, and bromine. Here, I drew the same molecule again. So then here's our mirror. So to start off, we're going to draw our carbon equal distance from the mirror on the other side. Now, we're going to take our first substituent, in this case, chlorine, and we're going to draw it with the kind of opposite orientation on this side. So since here, the chlorine atom is going to the bottom right, in the mirror image, it will be going to the bottom left. Now, we're going to take the next one, fluorine. And since fluorine the substituent fluorine has the orientation of a wedge coming out at you, in the mirror image, it will have the same thing. Now, bromine. And like I said about the fluorine, since the bromine has the dash notation in the original, in the mirror image, it will have dash as well. And since our hydrogen does not deviate left, right, backwards, or forwards, it's just a straight line up. And now, as you can see, each atom is bound in the same orientation, just in a complete mirror image. In this section, we're talking about chirality. And now, a molecule is chiral if it has an enantiomer. A molecule is achiral if it does not have an enantiomer. And like in the last section, an enantiomer is a molecule in which the mirror image is non-superimposable. Here, in this molecule, we have 2 chlorine substituents bound to the cyclopropane. And this is the mirror image of this. So now, no matter how we rotate the red mirror image, it will never align perfectly with the original molecule. So here we rotate it 60 degrees, and as you see, the wedge and the dash do not line up, because wedge is coming out, dash is going in.
Next, we'll be talking about diastereomers. Diastereomers are stereoisomers that are not mirror image. They have the same molecular formula and same connectivity, but they're different molecules, and they have different boiling points and different melting points. These are examples of diastereomers. Here is a cis 1,2 dichloroethene. This is a 1,2 trans 1,2 dichloroethene. As you can tell, for diastereomers, they have to be cis and trans. Here are more examples. Here's a cis and here's a trans. And also, here's a cis and here's a trans. These are examples of stereocenters with enantiomers and diastereomers. The stereocenters are indicated with the red asterisks. The enantiomer of the tetrahedral, all configurations must be flipped. In a diastereomer of the tetrahedral, not all of the configurations must be switched, only 2 or 1.
Hello, today I'm going to be talking about the Fisher model. The Fisher model is real efficient for modeling molecules with stereocenters. First off, to know about the Fisher model is that intersections of horizontal and vertical lines indicate a carbon atom. So as you can see here, this would be a carbon atom, like you can see in the molecule over here. Second thing to note is that horizontal lines indicate atoms pointing outward, and vertical lines indicate atoms pointing inward. This is kind of like a bow tie. So the ends of your bow tie point outwards as the knots tied tight and points inwards. You can see that right here from translating this one to here, is that the carbon atoms in the center, these 2 point outward, the rest of the molecule and this end is right there, pointing inwards. Now over here, we're going to translate this molecule to the Fisher model, okay? So right here we have the same functional group, and down here. So this group right here is pointing outwards from this carbon. So it's pointing out like this, as the carbon bonds here are pointing inwards. So we're going to put this OH right here, and since this has 3 bonds right there, we know that it's also bonded to a hydrogen, so that hydrogen will go there. Likewise with this one, both the OH and the hydrogen are pointing outward from the carbon, and both carbon bonds are pointing inward. But since this one is on the opposite side of the molecule, the OH will go here, and the hydrogen will go there. And we're just going to do the same thing for the rest of the bonds down here. So OH, H, OH, H, OH, and finally our H bond.
What's up, guys? Okay, so the next thing we're going to talk about here is alkyl substitution. This is going to be important for the way the stability of different molecules works. So when we define alkyl substitution, we know it as the number of alkyl groups bound to the 2 carbons of an alkene. If we think back to a couple weeks ago, an alkene is going to be anything consisting of that double carbon bond. So in that instance, you have your double bond with your 2 carbons and the possibility of 4 different substituents coming off of those carbons. The way this affects stability is kind of in a linear fashion. As the substituents increases, the stability is also going to increase. So if we slide down here, we can know that since there are 4 different substituents, there are going to be 4 different options for how these things change. Our first is going to be the most stable. It's going to be the tetrasubstituted, where, as you can see, each one of these substituents is an alkyl group. Like I said, that's going to be the most stable of these conformations. Next on the list is your tri-substituted. Again, you have 3 alkyl substituents and 1 hydrogen. That's going to fall next in line in stability. Next we run into our di-substituted, and we have 3 different options here for these that also are ranked stability-wise. The first is going to be with the alkyl groups coming off of the same carbon. The second is going to be your trans-substituted, and your third is going to be your cis. If we think back again to last week with cis and trans, we know that our trans is going to be more stable because the cis has steric strain. So we want to keep those 2 alkyl groups as far away from each other as possible to maintain the most stability. And then finally we have our mono-substituted, where you just have 1 alkyl group and the rest are hydrogens. Alright, so next we're going to talk about optical activity. Optical activity is going to be important to know because we need to understand what makes each different enantiomer different. Enantiomers, like we know, are mirror images of each other, so a lot of their characteristics are going to be very similar. Melting point, boiling point, things like that are going to be very similar. So in order to tell them apart, we're going to look at the way they interact with a plane of polarized light. So that's what optical activity is. It's the idea that enantiomers interact differently in this plane of polarized light. We have D molecules and L molecules. D molecules are going to be molecules that rotate around that plane in a clockwise fashion, whereas L molecules are going to rotate in a counterclockwise fashion. So the last thing we need to talk about here from this chapter is this idea of racemic mixtures. So like we said a minute ago, each pair of enantiomers is going to work in different ways in the plane of polarized light. You're going to have one that rotates clockwise and one that rotates counterclockwise. So when we differentiate between those 2, we can deem one of those major and one of those minor, and that's how we tell the 2 apart. So this idea of a racemic mixture basically says that you're going to have equal parts of major enantiomer and minor enantiomer, and when you put those equal parts together, they're going to cancel each other because each one rotates in the exact opposite way. So those cancel and you're going to be optically inactive. That doesn't sound really right because these are chiral, but because they cancel each other out, they are going to be inactive. So in the instance when we don't have a pure racemic mixture of equal parts, in order to determine how optically active that mixture is, we're going to find the enantiomeric excess. It's super easy to find. You just take the specific rotation of that mixture and you divide it by the specific rotation of the pure enantiomer.
As you can see here, guys, this is a stereocenter. And that stereocenter is a central carbon with 4 different substituents, all bonded equal distances apart from each other.
Left you falling on the floor, headed for the door, went straight to Philadelphia. Oh no, what have I begun? Call my mother, said I love her, and another question.
We're done. We're done. We